Hi guys, I'm here on a brutally cold Martin Luther King Day weekend to talk a little bit about integrated rate laws, why we would use them, when we would use them, and when they'd be beneficial over the regular differential rate laws. All right, so let's get started. Okay, so the first thing you're probably asking yourself is, why another rate law? We just figured out these differential rate laws. We're just kind of getting hold of them. You know, one thing changes, the other doubles and quadruples, or doesn't affect it. It's really confusing, right? And we just got done with the differential rate laws, which everyone calls just rate laws. And it's like, now another thing. Like, it's always one more thing. But I promise you, this actually makes sense pretty well. It's a lot easier if you're in an AP calculus or know a little bit about calculus. Then these are going to look kind of a little bit familiar. They'll make a little bit more sense. But if not, you don't need any calculus. Don't worry about it. We just won't worry about why or how they were derived. Okay, so first things first. Um, to use the differential rate law, we need the instantaneous rates at different points throughout the reaction, right? We need to double the concentration. We need to see how that affects the rate, and we need to cut the concentration in half and see how that affects the rate. But finding those rates can be tricky and can produce some error and can be a little tedious, especially in the lab. And you're going to be doing labs with this, and so there's an easier way to do it. All right, chemistry is all about finding an easier way to do things. Integrated rate laws are based off of a concentration versus time. And usually, it's really easy to measure concentration and time. All right, time is very easy to measure, right? Okay, it's a clock. Concentration, we can't measure it directly, so we're stuck measuring things like pH changes or color changes or conductivity changes or all these other things. But we're pretty good at finding concentration and being able to find a way to measure concentration changes. So we can measure concentration through probe wear or things like that, and we can measure time through a watch or clock. So they're very easy to measure, and it just makes things a lot easier. So I promise you, in the long run, it will make your life much, much easier if you understand the integrated rate laws. It's just going to be so much easier than trying to find the rates at a given concentration and blah, blah, blah. Plus, you don't need to do nearly as many trials, right? To find the differential rate law, let's say there's 2 reactants, you'd need 3 trials. Integrated rate laws don't work that way. You only really need 1 trial, and you can find it from there. Okay, so here's how we're going to convert. Now, what we're looking for is a straight line when we plot a graph. So you're going to plot 3 different graphs. One of them is going to be straight, and 2 of them won't be. The straight line tells you what your overall rate order is. Okay, so let's say, oh, I'm getting ahead of myself. So if I can find the straight line, I can find my overall rate order, and I can just plug that right into my differential equation. Okay, so let's say I plot concentration versus time. All right, so we would expect that graph to go down, right? As time proceeds, concentration will go down. If it's a straight line, it's going to be a 0 order reaction. It's going to be 0 order, and my slope is going to be my negative k value. Okay, so my k value is the slope, right? It's the negative slope because the line's going down, and k is a positive number. But all I need to do is just find my slope, which I can get off Excel, and there's my k, and I don't have to worry about finding anything. All right, let's say the natural log of concentration versus time is a straight line. Okay, so concentration versus time, it's not straight at all, but the natural log of concentration versus time is. Well, we call it, that's a first order rate reaction. And once again, the slope is my negative k value. So I don't need to worry about finding anything. I just plug in, find my slope. The negative of that is my k. And then last but not least is 1 over concentration versus time. If I plug that in, it's going to be, and if that's a straight line, it's a second order. Now this one's a little bit different because the line's going up, so my slope is just my k value. If you remember that k has to be a positive number, then you're not going to have to worry about if it's positive or negative k, but k is just positive. So just absolute value of it, you're done, you're perfect. Now this whole natural log and 1 over, these aren't random, they're derived through calculus, but we're not going to worry about that. All right, so we have concentration versus time, natural log of concentration versus time, and 1 over concentration versus time. So only one of those will be a straight line, and whatever the straight line is, that's your rate order. Okay, so now let's talk about the actual integrated rate laws themselves. So here's a little table. It's a little confusing here, but let's just talk about this for a second. So let's just look at 0 order. So at 0 order, R is my rate. It equals K to the concentration of A to 0 power? Well, we've talked about before how that's 1, so rate just equals k. Here's my integrated rate law. Now, it's a little bit more work. It's not as nice as r equals k, but it gives you a lot more power and information to do things. So the concentration at a given time, that's what that sub t means. So let's say the concentration at 50 seconds. That's going to equal negative k times that 50 seconds plus the initial concentration. A naught is the initial concentration. So if I want to know what the concentration is at 50 seconds, that's going to equal my negative k times that 50 seconds plus the initial concentration. All right, so that's nice and easy. And then it's this pretty much the same thing, except we toss in a natural log, and over here we toss in an inverse or 1 over. Okay, so let's practice that. All we're really doing is plugging and chugging. We're going to practice this a lot in class, and we're going to be doing labs with it, and it's a really important thing, but it's really powerful too, because if given the initial concentration, I can calculate what the concentration is at any given time. So let's try a practice problem. So I have a decomposition of sulfonyl chloride. Doesn't really matter that you know what that is. Whatever, that's fun. It's a first order process. So they tell you right now that we're going to be doing the natural log one. So we're doing the ln one. It's the first order. So the ln versus time is the straight line. The rate constant at 660K is 4.5 times 10 to the negative second. Okay, so they give you your K value. If we begin with an initial SO2Cl2 pressure of 375 torr. Okay, so we're dealing with pressure. That's fine. Rate laws work with pressure just as well as they work with concentrations. What will the pressure of SO2Cl2 be after 65 seconds? So 65 seconds is my time. Okay, so my rate law equation, I'm using first order, so this is my rate law equation. And I have K, I have T, and I have A naught, or my initial pressure. I'm just going to plug those in. Right? Oops, I dropped a negative sign there. Let me see if I can write that in. These never work very well. Let me write that in. That's a negative sign right there. All right, that's supposed to be negative. So the natural log of A equals negative KT. My K is 4.5 times 10 to the negative second. T is 65 seconds. Plus the natural log of my initial concentration. So your job tonight is to solve for the concentration of A. The concentration of A at 65 seconds. So you need to plug all those numbers in, and then you need to figure out, thinking back on your log rules, how do I get rid of this natural log of A, right? I'm going to have natural log of A equal a number. I need to just get A. So how do I do that? There's a log rule on it. I'm not going to ruin the suspense or anything. I want to see if you guys can do it. Okay, so that was integrated rate laws in a nutshell. I hope it's not too confusing. All I'm doing is graphing, looking for the straight line, and then whichever one's the straight line, that tells me what law I'm going to use. And then from there, it's just kind of plugging and chugging, and I can do a lot more with it. We use it because, one, it's easier to find, and it's just a lot more powerful of a tool. All right, I hope that cleared things up, and I hope you have a wonderful long weekend, and I will see you in class on Tuesday. Bye.